Hi everyone, this is Kavaljit Kurmi. I'm working as Principal AI/ML Specialist Solutions Architect. I've been with Amazon Web Services for almost 4 years now, and I specialize in containerized and machine learning applications. So today I'm going to talk about how AWS can help you build generative AI applications at scale in both managed and self-managed way. Now, the world of artificial intelligence and machine learning has witnessed a paradigm shift with the rise of generative AI applications. Now, generative AI, by definition, is a specific field of artificial intelligence which focuses on generating content. It could be human like text, it could be images, code, or even audio. Now, it has been proven that if you pick up a very large model and train it with massive amount of data with powerful compute, you will significantly boost the performance and accuracy of your deep learning models. However, there could be a couple of challenges when you do those large scale model trainings. And definitely the first one is hardware, getting access to and provisioning a new hardware and making your scripts adapt to that requires time, and you don't want to lose out on the performance benefits that that hardware could provide you. Secondly, you want to keep that hardware healthy to minimize disruption of your model training. And you need orchestration solutions as well, which could scale up your clusters, spin it down, and could make the security and network configurations work well. Data is one of the most time-consuming activities. Today, a lot of development efforts goes in storing, processing, and loading the data for machine learning training. And also, you need to plan for scaling up both your infrastructure and algorithms. Today, models are growing so big that they could not fit into one GPU memory. So you need to plan techniques like model sharding, where you can split your model across multiple GPUs and still be able to train the model efficiently. And finally, the cost. Training a large-scale model involves a huge cost, and more than ever, businesses want their teams to focus on adding value to the business rather than spending time in managing and maintaining the underlying infrastructure. And AWS is trying to address this challenge by providing you with a very broad and deep set of machine learning tools and services, which could be categorized into three different tiers. At the bottom tier, we have a broadest choice of high-speed networking, high-performance storage solutions, and powerful compute powered by NVIDIA, Intel, AMD. You can pick up the relevant compute for your traditional machine learning as well as your current deep learning use cases. Now, this is a place where we also offer AWS custom-built Inference chip powering Inf1 instances, which provides a very low latency, a low-cost inference, delivering up to 70% lower cost per inference. And if you're dealing with large models of size like 175 billion parameters, you could also use AWS custom-built Inference 2 chip powering Inf2 instances, which provides the best cost performance on the cloud, delivering up to 40% better price performance for generative AI applications. For large model training, AWS offers custom-built Trainium chip powering TR1 instances, which provides the best price performance of training large-scale models in the cloud, reducing the cost to train by almost 50%. To easily leverage AWS compute, in second tier, you can select from a broad set of cloud-based machine learning services, all the way from left, self-managed, where you can provision Amazon EC2 to spin up your virtual machines. You can use AWS Parallel Cluster for spinning up high-performance compute cluster. You can use Amazon Elastic Kubernetes Service and Amazon Elastic Container Service as your container orchestration solutions. You can also use AWS Fargate as your serverless solution, all the way to the right, where we have to offer you fully managed Amazon SageMaker service, which can help you build, train, and deploy your machine learning models through a single IDE environment called SageMaker Studio. And at the top tier, we offer AWS Deep Learning AMI, Amazon Machine Images, and AWS Deep Learning Containers to accelerate your machine learning in the cloud. So why deep learning AMI and deep learning container? It's because machine learning stack is very complex. So on the left, for example, if you're working with PyTorch, you have to install the optimized version of PyTorch and its required dependencies. You might also need CPU and GPU libraries for accelerated math and inter-GPU communication. You would also need NVIDIA drivers, which should align with the GPU compilers that you have used to compile the GPU libraries. And also, if you are doing a large-scale model training, you would need a network stack which is optimized and could provide you with the lowest latency and highest throughput. Now, AWS helps reduce this heavy lifting on your part by offering you a curated and secure set of these pre-packaged frameworks and dependencies through AWS Deep Learning AMIs and Deep Learning Containers. which are optimized and tested on EC2 accelerated compute instances, and which allows you to run your deep learning models very easily, giving you the best performance possible at zero cost. Okay, so this takes us to the use case. In this, we'll implement a hybrid architecture where we'll explore the art of the possible and we'll train and fine-tune a stable diffusion model in a self-managed way, leveraging Amazon EC2 with AWS Deep Learning AMIs, and we'll use NVIDIA-powered P4D compute instance. And we will deploy the model in a managed way using Amazon SageMaker service. We will leverage AWS Deep Learning containers, and we'll deploy it on NVIDIA-powered G5 instance, which provides us with 810G Tensor Core GPUs, as well as on AWS Inference chip powering Inf2 instance. So this will manifest the broad option of compute and ML services that you can pick and choose depending upon your organizational requirements. So with that, let's switch our screens and look at the demo. Okay, so we are on our AWS console. Here I have spun up an EC2 instance. And if you see, this is the AMI ID, which is a deep learning AMI that I have used. It is a P4D 24x large instance. And you can spin up this instance either using AWS CLI or directly from the console or from any of the SDKs that AWS provides. So once this EC2 is up, I'm going to go back to my terminal and I'm going to SSH to this instance. Right. Once I am in the instance, I'll just have to type in Jupyter Notebook, and this will bring up my Jupyter environment. There's one other thing that I have to do. I have to open up a SSH tunnel, which will allow me to connect my local port to the remote EC2 machine through Scale Channel. And then we'll switch back to our browser to open up the Jupyter environment. Okay, so we are in Chrome browser. So we have hit our local host, and then this will bring up a Jupyter environment. And I will be opening up Stable Diffusion for fine-tuning. Okay, so in this notebook, we'll be training a Stable Diffusion model. Basically, we'll be fine-tuning it. A Stable Diffusion is a model which is created by stability.ai and is now open source for everyone to use. Before we go into the code for fine-tuning, let's look at the architecture of Stable Diffusion. Now, what makes Stable Diffusion so special? It's this combination of three different architectures. One is when an input image is fed in from here on the left, we use an encoder-decoder model, which will be used for perceptual compression. Now, this is a model which will project the high-dimensional image from the pixel space to a low-dimensional hyperspace called latent space, which is basically a compressed version of that image. So once that compressed version vector is created, that vector will be passed through the forward diffusion process, where we will keep adding noise to that image until it become a complete random noise. Secondly, we will also use a text transformer, which will be able to understand the semantic structure in the data. We'll be using a clip text model in this particular case. And finally, here, this is where the denoising, the reverse diffusion process happens. We are using a UNet model. It's a U-shaped encoder-decoder model, which will predict the noise, and we will remove that noise to recover our original data, right? And we'll be using Hugging Face transformer and diffuser libraries to get the pre-trained Stable Diffusion model. You can get any kind of diffusion model from these libraries together with the scheduler, and you can build up your own diffusion pipelines. And we'll be using Hugging Face dataset library to load the Pokemon images. So we're going to be fine-tuning our Stable Diffusion with Pokemon images. This is how those images look like. Okay, so this is a place where we'll be loading the pre-trained model from Hugging Face library, right? We're going to be loading text encoder, variation autoencoder, and UNet, and we're going to freeze the parameters for the first two models. And we're going to use Adam optimizer here. And finally, when the training will happen, we're just going to go directly to training. If you see here, we have set the variation autoencoder and text encoder in the eval states because we're not going to train them. We're only training UNet. And when the training loop will happen, we're going to continue adding noise until it will become a random noise. And finally, we'll use the clip text model to generate a text embeddings of our input text. And finally, we'll feed it to UNet model for predictions. And then we'll calculate loss. We will run backwards through our network layer, where we'll compute the gradient, and then we'll use optimizer step to update our parameters. right? So this training will happen here. We are training it in 100 steps in just one epoch. This is a hello world example. Even this small training is pretty efficient, and we'll see the results very soon. Once the model training is done, we'll use Stable Diffusion pipeline to save our model in the local directory. And then once it is saved, you'll have to create a tar.gz file and push it to S3. Now we'll go to our inference notebook here. So in this case, we'll be using SageMaker. So right from the EC2, the same Jupyter notebook, we'll be calling the SageMaker library to deploy this model on SageMaker endpoint. Okay. So here are gonna 3 steps. First is we're gonna create our custom Hugging Face inference image. We'll create a Hugging Face model where we'll point it to the S3 location where we'll be pushing our model artifacts to. We'll pass in the image URI and a SageMaker session. And then the kind of infrastructure that we want this model to deploy on, this is the NVIDIA powered G5 instance. So the estimator that this model will be returning, we'll just gonna call deploy method, and we'll deploy that model on this infrastructure on SageMaker. So this is that simple. So just with 2 steps, you're able to deploy a model. And finally, we'll be using the SageMaker Boto 3 client to invoke this particular endpoint that I have just created before this session. So let's probably type in here our green Pokemon, and let's see what this model will generate for us. Okay, so we have a green Pokemon generated here. Let's probably customize it even more. Let's say playing, right? So there's a green Pokemon playing in a snow. So you can play around with this model. So this shows how easy it is to fine tune our Stable Diffusion on EC2, and how you can deploy to SageMaker for model inferencing. Now, in the second use case, we'll be deploying a model on SageMaker using Inferentia 2 based Inf2 instances. Right, so here we will be using the large model inference container, which is optimized for hosting large models using DGL serving. And DGL serving is a high performance universal model serving solution, which is powered by the Deep Java library. This is an open source solution, which is language agnostic. So we'll be using this container to deploy a model. We'll start with the boilerplate code where we'll import SageMaker libraries. And finally, this is where we will be loading a compiled model. So once you use torch neuronx trace method, you can use torch jit save and load method to save and load the models. So here we are just loading all the 3 architecture components of Stable Diffusion model, as you see here, decoder, and then we'll do it same for a unit as well. And finally, once these models are loaded, we will be using the Inferentia deep speed image that we have talked about. And finally, the 3 steps will follow to deploy it on SageMaker. The first step is we'll create a model which will point to the artifacts, S3 artifacts, where our compiled model is saved. And we will then create an endpoint configuration. We will define the infrastructure where we'll be deploying a model. If you see here, we are using Inf2 instance. And finally, we'll use the Boto 3 SageMaker client to create our endpoint. And once the endpoint is created, then you can actually invoke that model. So let's use a different text here. For example, let's use mountain and see if we are able to get some output. So if you see here, a nice a landscape is created. Let's probably modify it further. I'm playing with a ball. So you can try out and customize it further, and you can see how this model generate the output. This concludes the demo. So we'll be switching back to our slide. Okay, there are a couple of references which I want you guys to take away. One is our Neuron documentation, which talks about the AWS Neuron SDK, which you can use to compile and load the models on Inferentia chips. You should also look at Hugging Face Optimum Neuron library, which is an interface between the Transformer library and AWS accelerators for AWS Trainium and Inferentia. So hopefully you have found this content interesting. We will see you in a deep dive session on these topics very soon. Thank you.